Mandogne en mi glog. Patequele his mi reloj. Yo sé que tanto me costó. ¿Qué pasó? What's up, amigos? I'm going to make a very quick video today because I don't have a lot of time, and this is definitely not a problem that requires a substantial amount of time to solve. Go Bears. You know, the shirt I'm wearing right now, not that anybody cares, it's kind of big because I used to be kind of chubby. So if you ever lose weight, it's always interesting when you put on your old clothes. But that doesn't matter. Let's go ahead and get right into this problem. So you're given three positive numbers, A, B, and C. Return the minimum flips required in some bits of A and B to make A or B equal to C. Okay, so what's going on? We're given A, B, and C. And the constraint that we want is we want A or B equaling to C. Okay, what does that really mean? Well, if we looked at the truth table for A or B, let's go ahead and do that quickly. Thinking about what color to use. Okay, if we have a value A, a value B, and we want to find the evaluation of A or B, since we're looking about bit operations here, right? Bitwise OR operations, we should probably know, even before we continue, how does an OR operation work? So we have A or B. Now, there's only four possible things that can happen when you do a bitwise operation, right? Either B is 0 and A is 0, or B is 1 and A is 0, or B is 0 and A is 1, or they're both 1. Now, the result of A or B is, if one of them is 1, it's 1. If none of them are 1, it's 0. Okay, so since neither of them are 1, A or B would result in 0. Since one of them is 1, it results in 1. Since one of them is 1, it results in 1. Since one of them is 1, it results in 1. Okay, so this is the fundamental truth table that you should probably know if you're going to be approaching a problem that, you know, talks about OR operations or AND operations or XOR operations or whatever, right? You should probably know your truth tables, okay? So flip operations consist of change any. Sometimes these problems aren't written well, or maybe I'm not reading it right. Flip operation consists of change any single bit. You can change any single bit 1 to 0, or change a bit from 0 to 1 in their binary representation. Okay, so I can take a bit and convert it to a 1, but that costs 1 point, right? Or I can take a 1, convert it to 0, it costs 1 point. And my goal is to take A or B and make it equal to C. Okay, so in this example, we have, por ejemplo, for our example here, we have A equals 2, B equals 6, and C equals 5. Now for this, right, you're gonna need to write it out in its binary representation because this isn't really gonna give you a lot of information, right? So if we thought about what A was, it's 2, so that's 2 is 0, 1, 2. B is 6, so B is 6 is 0, 1, 1, 2, 1, 4. So then we'll add some padding here. And then C is 5. C is a 4 and a 1. Okay. So a C is a 4 and a 1. All right. So how's this going to work? Well, we want C to be 1 here, right? We need the OR to be 1, right? Because the 0, 0 is going to give us 0. So this 0, 0 is going to result in a 0. So in order to convert it to a 1, we're going to have to do what? We're going to have to change at least one character to a 1, right? So we're going to convert this to a 1, which is going to cost 1 point, right? Which makes sense. And you might be asked to say, well, if they're both 0, should I convert this one to a 1 or this one to a 1? Well, it doesn't really matter, right? Because when we're looking at these bits, it's like a separate problem every single bit, right? Every single bit we look at vertically is its own unique problem that we're going to consider in the solution, right? If I change this one to a 1 or this one to a 1, it doesn't matter because next we're going to be looking at these bits, and then we're going to be looking at these bits to make the calculation, right? So we don't need to be thinking about like, oh, should I change this one to a 1 or this one to 1? We just know that we need to change one of them a 1 in order to make this 1, 0, 1. Okay, so that's plus 1. How about here? Well, here we need the result to be a 0. So if we convert this one to a 0, because we know for sure that 1, 1 is going to give us 1, right? So if I convert this to a 0, it's 0, 1 gives us 1. But if I convert the other one to a 0, then you have 1, 0 gives you 1. So the only way you're going to make this 0 is if you convert them both to a 0. So that's going to give us plus 2 operations. All right. Now when we look at this, 0, 1, 0, 1 gives us 1. So we don't need to change anything plus 0. So then if we sum this together, we get 1 plus 2 plus 1 equals 4. Oh, I don't know why I did 1 plus 2 plus 1. 0 plus 2 plus 1, right? 0 plus 2 plus 1 gives us 4. So all we really need to do when we look at this problem is, well, we know that each of these bits are like isolated examples, right? They're isolated points that we're going to consider how much we have to add to our score to make this OR true. So let's actually just look at all A, B, C pairs and make decisions about what that means for the problem, right? So when we're looking at A, B, and C, what are all the cases that could happen and what would that do to our score? Okay. So if we have A, B, or C, what should that do to our score? So 1, 2, 3, 4. We'll call that our score S. Okay, so I'm going to iterate through all possible examples so then we can think about what that means for the solution, right? So 0, 2. I'm going to do a little thing I learned in college just to quickly iterate through all possible combinations of zeros and ones. So if we have A and B are 0 and C is 0, that's good, right? Because we want the OR to be 0, because the OR of 0 and 0 is 0. So that's good, right? So these are, well, think about the good cases here, right? 0, 0, 0, 0 becomes 0. So that's good. 0, 1 becoming, no, 0, 1 becoming 1, that's fine. 1, 0 becoming 1, that's fine, right? 1 and 1 becoming 1, that's fine. So the only ones that are problematic, so we can say there that this would be 0, 0, 0, 0. These ones are problematic, right? Because A and B are 0, but we want the OR to be 1. But the OR isn't 1. So what are we going to do? Well, we need to convert one of these into a 1. Right? If it's 0, 1, well, this 1 needs to become a 0, right? Right? This needs to become a 0. One of these needs to become a 1. If it's 1, 0, 0, well, we want A or B to be 0, so that's only going to happen if we convert this to a 0. And then this case we saw here, if they're both 1, well, that's not going to convert it to a 0. So I need to do both of them, so that's plus 2. Right, so this is our kind of resulting truth table here. This is what we need to consider. And we just look at each bit individually. And when we look at each bit individually, we make a decision about what's that going to do for the solution. Okay, I'm going to unplug my iPad because I'm noticing it's causing substantial delay. You know, so much compute for my computer. I probably need to get a new computer. But that's fine. So how are we going to do it? Well, first, we need to look at each individual bit. So how will we look at each individual bit? Well, what we can do is we can say, well, A or B or C, you can print the last bit. You know, we could do bitwise operations, or we can just do regular arithmetic operations by dividing by 2 and modding by 2, right? If you mod by 2, you get the last bit. So at the end, what we'll do is we'll say A divided by 2, B divided by 2, and C divided by 2. And if we want the value of A, the value of B, the value of C, we just do A mod 2, B mod 2, and C mod 2. So this will give you the last value, the value of the bit, the rightmost bit, and this will divide by 2 so you can, you know, walk through each bit, right? You'll look at this bit first, and this bit, then this bit, then this bit. And then we'll have a res, and this will do it for everything, right? So we'll look through everything to see what we need to convert. And then res equals 0 to begin with. We'll do some update to res, and then we'll return res at the end. So what's the problem here? Well, if C mod 2 equals 1, that's basically saying if the bit is 1, then we're going to add to res if A mod 2 equals 0 and B mod 2 equals 0. We're going to add 1 to res. What I'm saying here is if the last bit is 1 in C, then either A has to be C or B has to be C. I mean, if the last bit in C is 1, then either the last bit in A has to be 1 or the last bit in B has to be 1. Otherwise, we're going to add 1 to res. Else, in this case, that means that C is 0. If C is 0, then A and B both have to be 0, right? So I'm going to convert this here, right? And I'm just going to say res plus equal int A mod 2 plus int B mod 2. So what I'm saying here is this bit, if this bit's a 1, then we need to spend 1 to convert it to a 0. So we add 1 to res. If this bit is a 1, we have to spend 1 to convert it to 0. So we add that to res. And I can convert this into a similar code. I say we only add 1 to res if it's not the case that A mod 2 or B mod 2. So that's the same thing as saying if not A and not B. So if they're both 0, then we'll add 1. If one of them is a 0, if at least one of them is a 0, we don't have to worry about it. Okay? And then we just do this to res. We don't need this anymore. And then we're done. All right, and then let's submit. Okay. So what is the complexity of this? So let's say n is the max of A, B, and C. Okay, so that's the max number. Now we have to look at log bits, right? Because we have to look at the bit representation of a number. So that's the number of bits, and you can represent a number in its number of bits using log 2 bits, right? So we have to look at all log 2 bits. So for time, we're going to do big O of log of n. And then for space, well, we just create this res variable and then we update it appropriately. So that's O of 1. Okay, guys. I hope everybody has a wonderful rest of your day. Peace out.